equilibrium. When it's undergoing constant velocity. All right, let's try a simple example. A simple example, a car is being towed at a steady speed. The mass of the car is 1,500 kg, and the theta is equal to 0. So as you can see, it's been towed. This is my car here, and the line is just straight, and this is my truck. If I can draw that over here, my truck. It's unrealistic, but sometimes this is how they tow things. So what's the tension? What's the tension in the rope? All right. So if I label this here, I have my car. Oops. I got my car. I got my rope here. Now I want to know what's the tension. All right. All right. Same thing. Same thing we've been doing all video. All right. So I'm gonna move to red a little bit. So step 1, coordinate system. Same thing, guys. Nothing new. All right. Step 1, coordinate system. Here we have. Oops. Yes. First time that's straight. Plus y plus x. I don't need to change it. I think I'm gonna stick with the original to make it easier for me. All right. Step 2. Free body diagram. All right. Free body diagram. We have. So our object of interest is the car. All right. And the tension normally points in the direction of the pull, where the pull is coming from. So here the pull is coming from the truck. So our tension is going to point just straight horizontally in this direction. That's our tension. All right. And any other forces on the car, really? Well, the car is on the ground. So the gravitational force on the car is definitely existing. Yeah. And then because on the surface, you get the normal force as well. All right. So our free body diagram. All right. Step 3. Calculate the sum of forces in the x direction and the y direction. So I have f of x here. I have f of y here. All right. So notice we say we're moving at a steady speed. When we say we're moving at a steady speed, we're moving at a steady speed. When that's being said, you can simply assume it's a constant speed. And a constant speed is really constant velocity. So don't be surprised with what I'm about to do. So because we're in dynamic equilibrium right now. So anyway, what are the forces in the x direction? We have the tension. All right. And what are the forces in the y direction? In the y direction, we have the normal force and the weight. All right. Normal force pointing up in the positive y, and the weight is pointing down. Yeah. So now, okay, I'll say step 4. I can just simply do something here and say apply. Hold on. What we can do here is apply the equilibrium condition. All right, so 0 is going to be equal to T. 0 is going to be equal to the Newtonian force minus the weight. All right. So what do you want to find? You want to find the tension in the rope. So really all our tension is in the x direction. Thus, okay, hang on, am I doing this right? I have a car. Sorry guys, just want to make sure I'm doing it correctly. I'm gonna take a quick look at my notes. No, I apologize. In my question, I included friction. All right, I apologize. No wonder it wasn't making sense from. I included friction. So I'm gonna just do that really quick. I can show you how I can add that right here. So in the we have tension and we have friction. The car is gonna experience some friction. All right, and our friction here is 320 newtons. All right. So our free body diagram in the y direction, we have Newton minus weight, and we have tension, and then we also have friction. All right, minus friction. And then if we apply the equilibrium condition, friction again. So it's really the same. It's really the same thing. That we like. Nothing much has changed. Nothing much has changed. All I've done is added friction. So yeah. Now, what can I learn from this? Well, I know for sure that I'm in equilibrium. So my normal force, if I move my W across, my normal force is equal to my weight. That's for okay. So that cancels out. But also here, I move my friction across to the equal sign. My friction equals my tension. All right. And I know my friction. My friction is 320 newtons. So my 320 newtons is equal to tension. So tension is going to be equal to 320 newtons. And that makes sense, you know. We have the exact amount of tension that counteracts the friction the car is undergoing. All right? And that's allowing, so since this makes our friction basically equals 0. I mean, our acceleration in the opposite direction equals 0. So allowing us to move in constant velocity in the other direction. All right. Remember, friction always opposes motion. That's why it's pointing in the opposite direction. So now, if the tension is equal to the friction, they just cancel out. Like they just cancel out, and we have no acceleration in the y direction. So if I see my equation over here, this equation here, you know, I'm just gonna say 320 newtons minus 320 newtons. And it works. It's 0. You see that, guys? Mathematical phenomena, mathematical description of natural phenomena right now. So, yeah. Let's make it interesting. What if the car was towed at a steady speed at an angle? All right. So our friction is 320 newtons. Our mass is 1500 newton kgs, and theta is our angle. All right. Okay. So this is our car. Car here. This is our rope. Our rope. And then it's probably tied to a truck or something. All right. Just imagine there's a truck, a big truck from. Oops. Yeah. I hope you get the message here. Let's put this nicely for you guys. All right. It's been towed by a big truck at 30 degrees. All right, truck. Just to put that there to give you guys perspective. All right. Anyway, so let's get into it real quick. Oh, ball pen. Change my color. I'll change my color. Let's see. Yeah, sure. What the heck? So step 1. Coordinate system. Same things. Okay. Boom. Oh my God. Will I ever get a straight line today? Plus y plus x. Step 2. Free body diagram. Okay, I have a vector at an angle. So from there, I'm gonna. So from there, I know I have two different components of the vector. All right. So but anyway, my car is on the surface. So weight for sure, weight has its weight, but because it's on the surface, it's gonna have a normal force. All right. Yes. But then we also have an angle. All right. So we have the y component of tension in the y direction as well. So we're gonna have let's see. So we have a tension there. I'm gonna just put that as a tension. So now we have the y component of tension and the x component as well. The y component would be like right at where the normal force is. And this is going to be 30 degrees. All right, so the y component is right by the normal force as well, and the x component is right here. All right, so anyway, okay, step 3. Calculate the forces in the x direction, the y direction. Okay, so let me move this a little bit. Step 3. Forces in x and y directions. All right. So in the x direction we have, and the y direction what do we have? So in the x direction, we have positively we have the. I almost forgot my other guy. We have friction. In the next direction we have the x component of tension in the positive direction. And then in the negative direction, we have friction, like opposing tension, yeah. In the y component, we have tension in the y component, positively, and we also have Newtonian force, and we have the weight, not Newtonian, the normal force. Oh my God, I think I'm getting tired. Anyway, so now, because my car is moving at a steady speed, I know it's in a dynamic equilibrium, so I can apply equilibrium condition. All right, and I get 0 going to be equal to Tx minus F. All right, now here, guys, I'm going to do something that I'm allowed to do. All right, so I'm on a surface. All right, my normal force equals my normal force basically equals my weight because I'm on a flat surface. So because of that, the magnitude of my normal force is going to be equal to the magnitude of my weight. So every time I have n minus omega, I can assume that every time I have n minus omega, I'm on a flat surface. This is equal to 0. So the tension in the y direction, well, is not accelerating my it's not accelerating my car at all. So the Ty is 0. Boom. So we got that. Now what about the x direction? What's Tx? Well, we can decompose our vector. I'm not even going to get Ty because we know it's 0. So what's cos cosine. Oh my god. Anyway, so what's cosine? The adjacent, it's going to be tx. Okay, and then my hypotenuse, so it's ts, and my hypotenuse is going to be t. So tx is going to be equal to t times cosine theta. All right. And remember, we want to find the tension. All right, that's our goal. So I can plug in now. I can plug in. 0 is equal to t cosine theta minus f. All right. So now I can easily solve for t now. I can take f across to the equal sign. T cos theta divide by cos theta divide by cos theta. And boom, my tension be equal to my friction over cosine theta. And I know my friction. My friction is 320 newtons. And theta is what, 30 degrees. So I can plug in and get my friction. But once you have this equation, physics is done. In fact, some would even say physics is done somewhere here after applying the equilibrium condition. It's just math. So yeah, you know the friction, you can plug it in, and then you see the tension. And this should evaluate to about 340 newtons. All right. I think I saw this is an example in your book, so I think I saw the answer. Just solving it, 340 newtons. But you might ask yourself, wait, we have more tension than friction. What the hell is going on? You know? So if we have more tension than friction, well, if I'm moving in a straight line, yes, of course I'll be accelerating. But because I'm at an angle, I need more tension to keep it to keep the car moving at a steady pace. I need a little bit more tension than the actual amount of friction. So don't worry, physics still works. Newton did not lie to us. We have not disproved Newton. If I did, it would be pretty cool, but no, we have not. So the tension is more than the friction. You would think it's an acceleration, but there's no acceleration because we're at an angle. So we just need a bit more tension to keep the car moving at a constant velocity. So yeah. So I hope you enjoyed this series of applying Newton laws. Well, whether you don't enjoy it, I hope you know it's going to continue. We're going to work on apparent weight next. So yeah. Good night.